Okay, this is the force table lab. In the force table lab, you will add two vectors, in this case the two forces. So the vector, the force A, this force is represented by vector A, is the weight of this mass, and the force, which is vector B, is represented by the weight of this mass. So you have two vectors, and then you need to add and then check and experimentally with the equivalent if the total force that you come up with the theoretical value makes sense or not. So I'm going to show you how you can add two vectors theoretically in two different methods, so that you can check in experimentally. So let me show you here. There are two vectors here, vector A and vector B. So the length of the vector A is represented by this, the magnitude of the vector A is represented by this length, and then so on. The magnitude of the vector B is represented by this length, and the angle represents the direction, and so on. So these are the two vectors that you have to add. So two ways. The first way would be the component method. Let me show you here. The component method means, like, let's say you have vector, some vector A, then the vector A has x component in this direction and then y component in this direction, and then vector A can be expressed in terms of the components. So vector A, component of the vector A in the x direction would be A cosine theta, and then similarly this Ay would be A sine theta. Of course you need to have to use this sign convention. So going up would be positive, going to the right would be positive, and then negative and negative here. So you can use these components. Let's say in the component method, the vector A should be expressed in terms of the x component ax I plus ayj, and then in our example, in this vector A, the vector A is, the magnitude of this vector A is 10.3 and the angle is 150.9 measured from positive x-axis in counterclockwise direction. So vector A would be, the magnitude is 11.2, but when you get a component the way that I show you, you're going to have a x component negative 10 and y component positive 5. Similarly, vector B would be bxi plus byj, and then the component x component would be 7 and y component would be 4. Let me show you here. This is the vector, and the x component would be v, which is 7.1 cosine 45, and then y would be b 7.1 times sine 45. So that's the x component and y component. That now when you add them, the vector C would be the total vector. So you have to add the component, x component with the x component, and then y component with the y component. Then x component total negative 10 plus 7, negative 3, 5 plus 4, 9, and the magnitude would be the Pythagorean of these two, and it's 9.5. If it's the force, then it will be 9.5 newtons. If it is the velocity, then it will be 9.5 meter per second, and so on. So whatever the unit you are using for that vector. Right. And of course we are doing force here, so it will be newtons. So the angle theta would be tan inverse of the y component or x component of this resultant. It's negative 71.6, measured from clockwise from negative x-axis. But if you have measured the counterclockwise from positive x-axis, then you have to subtract from 180, and then 71.6. You subtract 180 minus 71.6, then you got this vector, this angle. So let me show you here. This is the x component, y component, the x component, y component. You see that this is negative because it was pointing towards left, and this is positive pointing towards up, and so on. Now that's the total vector. So when you combine the x and y components, you have negative 3x component and positive 9y component, and this represents the magnitude of the vector, and this is the direction of the vector. That's the component method. Now, how do you do the same thing in graphical method? So for the graphical method, you need to draw those vectors in a graph, and the magnitude of the vector should be drawn in terms of the length. So you have to have a scale. So in this particular example, it's 11.2 newtons. So I don't want to draw too long or too short, so that it looks it looks nice in the paper, so that you can read clearly, you can see clearly. So what you need to do is you need to scale in this particular thing. I would say 1 newton should be 1 centimeter, so that this vector's length should be 11.2 newtons. But sometimes your number will be very small. For example, if your number is 0.19, you just don't want to draw 0.19 centimeters. It's too small. So you might have to come up with this kind of scale that fits better in the page. So 0.1 newton should be 50 centimeter. Then you came up with this newton is 9.5 centimeter. So that would be the appropriate length. Or you can come up with any length, any scale that you think is better for your drawing. So how do you start with the graphical? How do you add the vector graphically? Your vector A is 11.2. Obviously, in my scale is 1 newton is 1 centimeter. So you draw 11.2 centimeter line at this angle because its direction is that. Now, once you have one vector, then again you need to, in the tip of the vector, you have to add another vector, the vector B, which is 8.1 newtons. So I'm going to put 8.1 centimeter length at this angle. Now this is vector A, this is vector B, and vector A plus vector B would be from starting to the tip. And this length would be the magnitude of the vector, sum of the vector, total vector, and this angle would be the direction. So now, you are going to get this magnitude in centimeters, but that's not the vector. So you have to scale backward now to get the newtons. So, get the length of the C, vector C, and the angle from positive x-axis. You need to convert centimeter to newtons. So backward in your scale, according to your scaling. This is the magnitude in newtons and the direction of the total vector, which is resulted. So I hope this can help you to conduct the experiment